Hello everyone, my name is Gupta and I am a PhD student at Northeastern University working in the Silicon Synapse lab. Today I'll be presenting our work on modeling and controls of fluid structure interactions in dynamic morphing flight. Here are the authors who contributed towards this paper. Professor Ramezani is my advisor and he leads the Silicon Synapse lab at Northeastern. Dr. Sihite is currently a postdoctoral researcher at Caltech. Let me start by introducing our platform, the AeroBat. This is a bat-inspired flapping wing robot that we have developed to study dynamic morphing wing flight. The key specifications are a 30 centimeter wingspan weighing just 30 grams with 2 degrees of freedom per wing. The gate cycle duration is approximately 100 milliseconds, meaning we can flap at frequencies up to 10 Hz. What makes AeroBat unique are its two primary wing degrees of freedom. First, theta p, the shoulder plunge angle, which controls the upstroke and downstroke motion. Second, theta e, the elbow flexion and extension, which allows the wing to expand during downstroke and retract during upstroke. It can be seen in this video. On the right, that is a hovering test where we have tracked the wing tip trajectory. So why are we studying dynamic morphing wings? Unlike insects, vertebrate flyers like bats manipulate fluid momentum in 3 dimensions. Bats can move over 40 joints dynamically during a single gait cycle. Their wings are also relatively heavy compared to their body, which means inertial contributions are significant, something we can't ignore in our models. This is precisely why quasi-steady aerodynamic models which work well for insect flight are inadequate for our platforms. The complex fluid structure interactions require unsteady modeling approaches. So our research goal is to expand AeroBat flight capabilities beyond simple hovering to include 3D trajectory tracking, especially banking turns and eventually sharp dives and complex landing maneuvers. So the key contributions of this work are fourfold. First, we developed a test platform combining AeroBat with a Kinova robotic arm for a controlled 3D path experiment. Second, we experimentally validated our unsteady FSI model, specifically for a banking turn maneuvers. Third, we designed a collocation-based controller for 3D trajectory tracking. And fourth, we provide a detailed comparison between simulation predictions and experimental force moment data. Our experimental setup. On the left, you can see AeroBat version beta mounted on the end effector of a Gen 3 6DOF Kinova robotic arm. The arm provides joint speeds up to 70 degrees per second and end effector linear speeds up to 50 centimeters per second. This allows us to emulate banking turn trajectories while the robot is flapping. Critically, we have integrated an ATI Nano 17 6-axis load cell at the interface between the arm and the robot. This transducer samples force and torque data at 7 kHz, giving us high fidelity measurements of the fluid structure interaction during flight. On the right, you can see a sequence of snapshots for our Bankington experiments. For our experiments, we maintained a constant pitch angle of negative 15 degrees. We varied the roll angle across 10, 15, 20, and 25 degrees and tested forward speeds of 0.7, 0.8, and 0.9 meter per second. In this total, we collected like seven data sets under these varied conditions. Now let me describe the unsteady aerodynamic model we use to predict fluid structures interactions. Our model is based on lifting line theory combined with Wagner's function. The key idea is to represent the circulation distribution along the wingspan as a truncated Fourier series. Here gamma of t and y represents the time varying circulations at position y along the wingspan. The Fourier coefficient an capture how the circulations evolves over time. The variable a0 is the lift curve slope, c0 is the chord length at the wing axis of symmetry, u is the free stream velocity, and s is the total wingspan. From the circulation, we can derive the induced downwash shown in the second equation, which accounts for the velocity induced by trailing vortices. The sectional lift coefficient follows from the On Kuta-Joukowski theorem, notice that it depends on both the instantaneous Fourier coefficients an and their time derivatives. This is crucial. The time derivative term captures the unsteady effects the quasi-steady models miss entirely. To model the state response of an airfoil undergoing a sudden change in downwash, we use Wagner function. The lift response is proportional to the downwash change delta W scaled by the Wagner function phi. We use Jones approximation for phi, which is expressed as this double exponential form. The coefficients are listed in the table, which is on the right side. Psi1 equals 0.165, psi2 equals 0.335, epsilon 1 equals 0.0455, and epsilon 2 equals 0.3. The normalized time t tilde is defined as the integral of the quarter chord velocity divided by the half chord length. This non-dimensionalization allows the model to correctly capture how quickly the flow develops around the wing during transient maneuvers. For flight control, we formulate a trajectory tracking problem with this cost function j. The optimization state G consists of the roll angle theta r, pitch angle theta p, and the angular velocity vector omega. We minimize the square error between the current state and our reference trajectory, weighted by a diagonal matrix C. The dynamics come from our computational structure model. The left side that you can see in the equation shows the state derivatives, positions, and velocities of n structural elements. These depend on the current state through matrix A, which encodes the physical properties like structure configuration and material properties. The input matrix B determines how the regulator input omega affect the structure. After temporal discretization, we get this compact form, which is shown on the top right. We enforce two types of constraints: boundary conditions Ri that ensure continuity of the computational structure across the gate cycle, and inequality constraint Gi that respect actuator limits. So to solve this optimal control problem efficiently, we use a collocation method based on polynomial interpolation. We first form a decision parameter vector y script that stacks all the states and regulator inputs at discrete time points, plus the final time tf. The optimizer finds all these values simultaneously. For the regulator inputs, we use linear interpolation between time points. For the states, we use cubic interpolation, which ensures continuous differentiability. The cubic coefficients C0 through C3 are computed from the state values and dynamics at the interval boundaries, as shown in these equations on the right. The key advantage of this approach is that we only need to enforce collocation constraints at the midpoints of time intervals. This significantly reduces the computational burden. We solve this resulting nonlinear program using MATLAB fmincon. So for our simulation, we used fourth order Runge-Kutta integration with a time step of 0.0001 seconds. The controller updates at 200 Hz with a 5-step prediction horizon. Aerobat flaps at 3.5 Hz, matching our experimental setup. The reference trajectory maintains a pitch of -15 degrees throughout. The roll angle starts at 0 for the first second, then transition to 15 degrees for the remaining 4 seconds to execute the banking turn. Total simulation duration is 5 seconds. Now for our results, this figure shows the force and moment trajectories over approximately 0.85 seconds, which corresponds to 3 complete flapping cycles. The red traces represent experimental data from all 7 datasets, showing the range of measurements. The black traces are our simulation predictions. Looking at the forces, Fx and Fy shows some variation between experiment and simulation, but the overall trends match well. For Fz, the vertical force experiment shows a range of negative 0.5 to positive zero point 0.5 newtons, while simulations predicts negative zero point 0.3 to zero point 0.3 newtons. Overall, the periodic behavior clearly matches the flapping gait. For the moments, the patterns are remarkably similar between experiment and simulation. The periodic positive moment in MOI indicates pitching motion, which is exactly what we expect for a tailless design like Aerobat. The key takeaway is that our on-3D model captures the essential dynamics of the force moment profiles during banking maneuvers. We also analyze the wake structure and vorticity distribution during flight. The figure A on the left is a 3D visualization of the vortex wake trailing behind Aerobat. On the right, we show vorticity plots in the frontal plane at four phases: beginning of downstroke and mid downstroke, when the robot is before banking turn and during banking turn. The key observation is this: before the banking turn, the vorticity distribution is symmetrical, indicating stable flight, but during the banking maneuver, an asymmetrical pattern develops across the wings. This asymmetricity is precisely what generates the differential forces needed to execute the turn. This slide shows the complete state trajectories and the resulting 3D banking turn from our simulation. On the left column, we have the linear position, linear velocity, and angular velocity, all in the inertial and body frames respectively. You can see the X position steadily increasing as Aerobat moves forward, with the Y position decreases as it executes the banking turn. The G position shows a gradual descent. In the middle column, we show the orientation angles and joint kinematics. The pitch angle shown in orange oscillates around negative 15 degrees with an amplitude of about 7 to 10 degrees due to the flapping motion. The roll angle in blue is the maintained precisely at 15 degrees after the first second, which enables the banking maneuver, and the yaw angle shows a smooth continuous change as the robot turns. The shoulder and elbow joint angles shows the periodic flapping pattern with the left and right wings moving in coordination. On the right, we have 3D trajectory visualization with snapshots of Aerobat at different time instants. Over the 5-second simulation, the robot covers 4.1 meters in the X direction and 5 meters in the Y direction. The key result here is that our collocation controller successfully regulates the actuators to achieve this smooth 3D banking turn while maintaining the desired orientation throughout the maneuver. To summarize our contributions, we successfully enhanced the FSI model accuracy for 3D path tracking. Our collocation-based control approach achieves banking turns in simulation. We demonstrated good agreement between experimental measurements and simulation predictions, and our wake analysis confirms expected aerodynamic behavior during maneuvers. For future work, we plan to improve the model for varied flight trajectories and incorporate wing flexibility effects. We want to expand to more aggressive maneuvers like sharp dives and inverted landings, and ultimately we aim to validate this on untethered flight with real-time onboard implementation. I want to thank you for attending my talk, and in the screen there is the contact information where we can reach out with any questions you have. Thank you so much.